There's a lot of talk about strengths and pH and properties of acids and bases, but where do they actually get these numbers from? How can we quantify it? Well, all it takes is a calculation. When we look at the dissociation of acids and bases, they always occur in water. Water is the means, it is the basis for these properties that we can use to predict. Therefore, when we want to quantify the strength, we have to look to water first. Looking at the dissociation of water, it will, because it's an amphoteric species, it will react with itself. One species of water will act as an acid and the other will act as a base. So we will form a hydronium ion and a hydroxide ion. When we go, and you can use the acid-base strength chart to determine the weaker side, and it favors the water side. So water is the weaker version of hydronium, the conjugate acid of the hydronium ion. So our reactants are going to be favored. We can also see this visual over in this image where we have this dissociation. So here we have that concentration, moles per liter, and you can see that with water on the reactant side, there's a much higher concentration present versus our hydronium ion and our hydroxide ion. So to figure out the values here, we work with our equilibrium expression, our equilibrium constant that we have used before. Specifically, because we're using water as our base species, it is called Kw, or the equilibrium constant of water. Remember, when we write our equilibrium expressions, we put the concentration of our products over the concentration of our reactants. And then we are going to put in our compounds. Now, going back to equilibrium expressions are only written for substances in their aqueous or gaseous state, not their solid or liquid state, because solid and liquids tend to have such a high concentration that we cannot measure any minute changes. But because gases can go into solution, same with aqueous can go between being aqueous and a solid or aqueous and a liquid, we can measure those properties. Therefore, when we look at the Kw, or the water constant, it only looks at our hydronium and our hydroxide concentrations. And so this is the equation that we need to look at. In pure water, we are going to have the same concentration because it's a 1-to-1 split. It is a balanced equation. What they have calculated and determined is that in pure water, the concentration of our hydronium ion is 1.0 times 10 to the negative 7. And our hydroxide ion concentration is also going to be 1.0 times 10 to the negative 7. So when we multiply these two values together, our Kw, the constant, is 1.0 times 10 to the negative 14. This value is going to be used as a standard. It is what we're going to compare our acid-base reactions to, or their dissociation for pH. This will be a number you need to know, as it's what we compare everything towards. We can use the water constant to determine the concentration of either a hydronium ion or our hydroxide ion that we can then use to determine if it's an acidic, basic, or neutral solution. If we know that our hydrogen ion concentration is 5.4, that's a 4, not a 9, times 10 to the negative 8. What is the hydroxide ion concentration? With the calculation that we had set up on previously, we know Kw equals the concentration of our hydronium ion and hydroxide ion. Remember, the hydronium ion and the H plus are one and the same. We just get lazy and write H plus. If we know Kw is a constant, it's going to be 1.0 times 10 to the negative 14. Therefore, as long as we know one of the other ion concentrations, we can find the unknown. Since we know our hydronium ion concentration to be 5.4 times 10 to the negative 8, we can then find our hydroxide ion concentration. So we're going to divide by that 5.4 times 10 to the negative 8. And that's going to isolate that hydroxide ion. So when you put this into your calculator, you're going to put 1.9 times 10, or the answer is going to come out as 1.9 times 10 to the negative 7. So remember, when using your calculator, it's a lot easier to use the EE function or the exponent function for you. So I'm going to put that 1.0, and then remember, we're going to do second, and then EE, which is above that x to the negative 1. So that E means times 10. So I'm going to put the negative 14. Because of the way the E is designed, we don't have to put that number in parentheses. So I'm going to do 5.4 E negative 8. So I have that calculation set up within my calculator. I'm going to hit enter. It's going to give me that value. Now you can go through and change that into scientific notation, but remember, you can hit the second, and then where it says psi, right here with the DRG, and go over to scientific, and it's going to put it into scientific notation. You want to make sure that you still have the correct number of sig figs as well. This, using the E function, is going to save you a lot of time and heartache with exponents, especially these kind of exponents, versus doing times 10 caret negative 14, because if you don't put parentheses, and then different rules apply with your PEMDAS of what you can go through and calculate. So make sure that you are confident and comfortable in working your calculator and that exponent function for scientific notation. So how do we go from the water constant to the pH, and how are they related? Well, pH represents the acidity of the solution, so it's an easy way to infer the concentration of hydrogen and hydroxide ions. pH literally means the P stands for the potential of, and the H is hydrogen ions. So what is the potential of finding hydrogen ions? Therefore, the acidity of that solution. The pH scale is much easier to read and interpret than the really small numbers and exponents. And so for the common consumer, pH gives us enough information to communicate the acidity or basicity of a solution. The range is from 0 to 14. When you have a pH less than 7, and really we go around 6.5. What that tells us is that we have more hydrogen ions present in that solution than hydroxide ions. So if we take that back to concentration, the hydrogen ion concentration is going to be getting closer to 1 because the exponent roughly represents the pH value. So if we have 10 to the negative 6, the pH is going to be around 6, all the way up to the value of 1. For a basic solution, that is going to be a solution that has a pH greater than 7, and again about 7.5, because we like that neutral zone to be between 6.5 and 7.5 to allow for an interpretation or the lack of precision of our measuring devices. But if it's basic, we're going to have more OH ions than hydrogen ions. So that means that there's going to be less H+, more OH. So here, we would expect to see like 10 to the negative 9 for our hydrogen ion concentration because that pH is going to be 9. Where the OH concentration would be closer So if we added it up to 14, doing math on the fly, it would be 10 to the negative 6, right? That's 15, not 14. 10 to the negative 5. So you can see how it goes back and forth. Nope. Yeah, 8. To make sure that our exponents always equals that magic number of 14, and we have that ratio. But the concentration values are not useful for consumers. They're going to be useful for us because it tells us the details of that solution. Because when we are working with living systems, like our blood pH can only range between 7.35 and 7.45 before you have medical issues. So knowing the details of that concentration is absolutely essential. But for the common consumer, we can just use the pH values as well. So what does pH actually mean, and what scale are we working on? pH is a logarithmic scale. When we look at the calculation for pH to go between concentration and that pH value, we take the negative log of the concentration of either the hydrogen or hydroxide ion we are looking for. Well, hydrogen ion concentration. What does this mean? Well, log base 10 is the most common form of the logarithmic scale. It allows us to look at the exponent function in a whole number. It makes it easier to interpret. So if we are working with the number 100, its exponent form is 10 to the 2, which means it has that power of 2. So if we have the value in a ones place, we know we move that exponent, or sorry, that decimal twice, and we get that 100. So when we go into the logarithmic form, that log base 10, we don't write the 10, that's the logarithm that we're using. We put that concentration, and you can even actually put 10 to the 2 in there as well, and it will work because it means the same thing. 110 to the 2 is the same value. But what it does is it brings that exponent down into a number value. So that number value can give us an idea of how many powers of 10, so how many times we need to move a decimal to represent that number. Because it's a log base 10 or a power of 10, one pH unit change corresponds to a 10-fold change. That means if we have a pH of 4 and it changes to a pH of 5, what we are saying is this was 10 to the negative 4 to 10 to the negative 5. We have moved that decimal one time smaller. So we've moved it by a value of 10. And then if we go to 6, that's going to go to another value of 10. We're moving the decimal yet again to 7, so on and so forth. It's just like when we do the metric prefixes, kilo, hecto, deca. King Henry died by drinking chocolate milk, and we're moving. Same concept here. For each time we change that pH, it changes by a value of 10. So when we change a pH twice, that's 100 times change in concentration. 3 times, 1,000 times change in concentration. Now, specifically with pH, because our exponents are negative, we have to take the negative log in order to create a positive number. So that is why, for us, it's the inverse of the exponential function. It's bringing that exponential function as a positive value down into a real number. As we go between pH and concentration, we have to watch our sig figs. But because it's a logarithmic scale, sig figs rules are slightly different. So the number of sig figs in the concentration, so if we have 1.2 times 10 to the negative 4, that is going to equal the number of decimal places in the pH value. That's why you don't just randomly do things, because then you don't know what the number is. 1.2 times 8 to the negative 4. And so that's going to give us 3.9208, blah, blah, blah. So it's going to be 3.92. It is 2 decimal places is what provides us that 2 sig figs that were in the concentration. If you're a person who really needs a deeper understanding of why this exists, there is an optional video cast on why the sig fig rule exists. It's not going to be required, but it helps explain that there is a reason behind this significant rule. Here are the series of equations you need to know and be able to apply. I would recommend just memorizing one set and then know that with hydrogen versus hydroxide, it's going to be the same process. What we have on this first line is we've got, or where we are working specifically with the hydrogen ion concentration. This is used most often because this is what the pH scale is based off of. Based on what it is you're looking for, you can find that unknown. So if we know our hydrogen ion concentration, we can use the negative log of that concentration to find that pH. If we know the pH, we can take what's called the anti-log. So the anti-log is 10x. It's going to be right above the log button on your calculator. So you want to use that 10x. You do not use 10 caret. Does not mean the same thing. So this brings us out of the base. So essentially it's taking the pH and turning it back into that exponent value. All right, so we can take that pH and figure out the actual concentration so we can make changes to the solution as necessary. The same process works if we are working with our hydroxide ion concentration. The pH scale is not as often used because it's just equal and opposite of that pH. So if you remember the two calculations for pH, they're the same for pOH. Then we have the two equations that allows us to communicate between pH and pOH. Because they are two different entities, two different ions, they do not convert together easily. So if you're in your concentration form, you can use the kW because the kW is a set value at that 1.0 times 10 to the negative 14. If you're in the pH, because that 14, that exponent becomes a whole number, you can just take 14 and look at the pH and pOH. So it feels like a lot's going on here, and there really is not. What you should do when you're approaching a problem is make the map. Know what you are looking for and how to get there. So let's say we know the concentration of hydrogen ion. And we are looking for the pOH. Make a map so that then you can perform the calculations that are necessary. So if you know your hydrogen ion concentration, you could go directly to pH by doing the negative log of that hydrogen ion concentration. Once you're in your pH, you can go to your pOH by using the 14 equals pH plus pOH. And so you can follow your steps. Or if you know your hydrogen ion concentration, you can go to your hydroxide ion concentration by using the kW calculation and taking kW divided by your hydrogen ion concentration. Now that you have your hydroxide ion concentration, you can go to your pOH by taking the negative log of it. Both will get you to the same place. My suggestion is figure out if you prefer working with exponents in the kW or if you'd rather work in the logarithmic scale of pH and pOH. Because they'll get you to the same place. It's just how confident are you within your calculator of working with exponents versus whole numbers. Making this map will help you orient your understanding of how to get from what we were given to what we want to know. Let's run through some calculations. All right, so if we know the hydronium ion or hydrogen ion concentration to be 3.2 times 10 to the negative 9, what is the pH, pOH, and hydroxide ion concentration? So you can go through this a couple different routes, right? So solving the first one. So to solve for the pH, that is going to be the negative log of our concentration. So So when you plug this into your calculator, for these TIs, you're going to do negative, and then you're going to hit the log function. So you have negative log, and then you put that concentration. Use the E function for your scientific notation so that it goes in correctly. You're going to hit enter, and that's going to give you your value. And it's going to give you more than we ever need, right? So we have to watch our sig figs. Because there are 2 sig figs in our concentration, there are going to be 2 decimal places occupied within our pH. So we're going to get 8.49. All right. Now, depending on your calculator, you may have to learn how to enter this in. So if you have just the TI-30, not the TI-30X2, you actually have to go backwards. You enter in the exponent function, log, and then the negative. So take the time, learn your calculator so you can enter this information in correctly. Now to find the pOH, I can take 14 pH plus pOH. So I can take 14 minus 8.49, and that's going to give me my pOH. And so that's going to be 5.51. Same, because it's, pardon me, addition, subtraction. This is really actually 14.00, but because this is a constant number, it's not a measured number, so that's an exact value, so we're going to be taking our sig figs from that measured value. Now that I have my pOH, pardon me, I can do the antilog of my pOH. So the anti-log is going to be above your log button, so second, and it's going to give you that 10 carat. That 10 carat is vastly different than you typing 10 carat. You've got to use the anti-log function. So I put 5.51 in there, and I'm going to get a ridiculous, negative 5.51. I forgot my negative. And then you're going to get a number. Again, if you want to convert this to scientific notation by hand, you can do so. Otherwise, you can use your calculator's function to put it into scientific notation. So I get 3.1 times 10 to the 6th, negative 6, sorry. And so we have those 2 sig figs that we had started with at the very beginning, also from this the 2 decimal places. You could have taken the kW, so the 1.0 times 10 to the negative 14, and divided by the 3.2 times 10 to the negative 9th to then get that same answer. So like I said, find a route you like, stick with that route, and let it work.